Today, we'll talk about building an MMO system, massively multiplayer online, that can support thousands or even millions of players. First, let's consider what an MMO system needs. We can leverage everything provided by Unreal Engine, but not all games require all these features. Sometimes the requirements should be defined by the specific design of your game. Every choice to include or exclude a feature has its own pros and cons, and using everything may not be the best fit, so it's essential to consider carefully. For example, in a game like Minecraft, which focuses on creativity and collaboration, it's necessary to synchronize each player's position and actions in real time. However, if the goal is simply to show that the server has many players, then updating player positions and actions every few seconds can be sufficient. In games with a high player count, sometimes only loading a subset of players is enough. If the focus is on social features, like in Splatoon, you can sample a subset of players to display their gear setups and place their characters in fixed poses at specific locations. Beyond these considerations, there's an important question of handling system crashes. We need to define our crash handling strategy based on whether this MMO system is crucial enough to require continuous online availability and whether the system's data impacts the game. This will influence the way we implement the MMO system. For instance, if the MMO system is essential for players to access the game, then we'll need a backup system and auto-scaling services to ensure it's always online, along with a serverless database to prevent data loss. Alternatively, we could look into a fully serverless solution, such as one using an AWS database paired with AppSync to provide a GraphQL web API. Before we finalize a solution, we need to think through a few other points. An MMO system obviously needs to support a large number of players, which will bring varying performance requirements depending on the number of concurrent users and a high demand for network bandwidth. So estimating the costs, specifically the average cost per player per minute, is critical. Some designs can achieve a lower average cost when serving more players. For example, in a relational database setup, adding a Redis or Memcache database for quick data access can speed up query times, reducing the average cost. However, when the player count is too low, adding an extra database could increase the average cost instead. Therefore, accurately estimating the player range is another crucial factor. At the same time, an MMO system is a long-running system, so stability is an essential metric. There are various ways to measure stability. In general, we can use a metric borrowed from the hard disk industry called MTBF, mean time between failures. It represents the average hours before a failure occurs. For instance, if you have a program running on 10 instances and one instance fails after 100 hours, then the MTBF would be 1,000 hours. In a production environment with 100 instances, you should prepare for a failure about every 10 hours. In a multi-program system, we also need to consider the lowest average time between failures across programs. For instance, if one program with an MTBF of 10,000 hours runs 10 instances and another program with an MTBF of 20,000 hours runs 100 instances, the former would have an effective MTBF of 1,000 hours and the latter 200 hours. In this case, the overall system stability would be an MTBF of 200 hours. So before releasing a game with an MMO system, we should estimate the BTMF to prevent frequent crashes, which could lead to user attrition. Another key point, and arguably the most important, is maintenance. As the user base grows, so does the overall cost. At this stage, we might consider switching to a different MMO solution. For example, if we started with a real-time data solution when the player count was low, we might want to switch to a non-real-time solution that only displays a subset of players when the player base becomes very large. We may also need to review the code to troubleshoot bugs. Thus, it's not enough to only pursue low average user cost and high stability. We also need to think about maintenance difficulty and cost. We should choose solutions with significant market share, like Fast API, which is based on Python and used in this tutorial. Let's now go over a few popular MMO system design solutions. The first is a dedicated server using Unreal Engine. This approach allows us to easily implement a real-time MMO system. However, it requires significant performance calculations for things like character collisions and movement, making it one of the most costly options per user. Due to performance demands, some developers opt for a solution that uses multiple servers to handle a single map, dividing the map into zones that each run on different servers and synchronize player information across them. While this approach may help performance, it's neither cost-effective nor very stable. Using multiple servers decreases the MTBF For example, if a program originally has a 10,000 hour MTBF over a year, distributing it across 20 servers reduces the MTBF to just 500 hours, or about 20 days. Handling crashes also requires that each server has a backup, but often a single server failure can cause the entire system to crash. Repeated game crashes or extended downtimes lead to high player attrition, rendering marketing efforts ineffective. For these reasons, we generally don't recommend this method. Instead, we can use a simple collision map as the server map. A simple collision map is built from basic collision models, like cubes and cylinders, which covers the models in the original map. This map is then treated as the main map on the server, with collision set to no collision for the original map's shapes. On the server, only the simple collision map is loaded, while the client loads sections of the full model map based on player position. This way, the server only needs to process collisions for simple shapes rather than complex models, saving significant resources. In most games, interactions with the environment involve collision objects. For example, in Minecraft, when you break a block, it's the collision detection identifying the block in front, while the model and textures only appear in client-side animation. So only the simple collision shapes are loaded on the server, while the client loads the detailed models and textures as needed. This approach effectively reduces the average cost per user. Using Unreal's dedicated server makes it straightforward to create an MMO game with player environment interaction. However, this solution still has one of the highest per user costs. Another approach to building an MMO system is to use a database with a web API created via API Gateway or AppSync. This works similar to what we discussed in the previous video. We can use the web API to update or query player positions at intervals, like every 5 seconds. Although not real time, it's relatively cost effective and can display many players on the map. Alternatively, we can create a real-time MMO system using WebSocket. This method, particularly in a serverless setup, offers the best stability and is cost-effective with lower player numbers. However, as the player count grows, query and pagination times increase, resulting in higher database costs. To mitigate these costs, we could add a front-end immutable database, ledger database, and a back-end in-memory database to reduce load. Of course, this also incurs some capacity costs, but setting a time to live TTL for the data can help reduce redundant information. This solution causes the average cost to fluctuate significantly with player numbers, so accurate player count predictions are necessary. If a more stable cost structure is desired, we can run a web application on an EC2 instance to provide the web API. This results in stable pricing, where an increase in player numbers only slightly raises bandwidth costs. Additionally, we can add an in-memory database or use the EC2 instance's memory to store data. This setup mainly uses memory as the primary storage method. So if the system crashes, data will be lost. Regular backups of in-memory data can be done once a day. When the number of players reaches the EC2 instance's capacity, auto-scaling can increase the instance count. Using a serverless in-memory database can provide persistent storage as well. For minimal costs, we can randomly select a certain number of users from the Cognito user pool and assign them to fixed positions or present paths. This enhances social interaction by allowing players to interact with each other's characters and view equipment in a way similar to Splatoon, where players are fixed in place, making it easy to add friends. The best part is that this approach incurs almost no cost. In this video, we'll use a web application approach, using Python with Fast API to create a WebSocket-based MMO system. We'll start with a RESTful web API for health reporting, enabling the load balancer to ensure the application status. Next, we'll create a RESTful web API to retrieve online players and a WebSocket API allowing players to update their location and other information in real time. We'll also create a WebSocket API for other players to subscribe to real-time location updates. Similar to the friend system in the last video, we'll authenticate location update requests to ensure data integrity. To reduce average cost, we'll limit broadcast frequency by adjusting a variable's value. For a real-time MMO, we could set this interval to 0 for immediate updates. Here, without demonstrating a dedicated server setup, the client will load directly into the gameplay map after login. To avoid cluttering the screen with all online players, we limit the number of players displayed. We'll calculate the number of online players to display on the map while excluding the current player and those already visible. We'll use a RESTful request node to query the rooms Web API endpoint for online players, and for each retrieved player, we'll spawn an AI character. The AI can make player movements appear seamless when data isn't received promptly or for non-real-time systems. Each AI player subscribes to the WebSocket API to receive real-time location and information updates. When a player goes offline, we also use AI to remove the corresponding AI character. The client-controlled player character will subscribe to the WebSocket API for real-time position updates, sent every 5 seconds to save bandwidth. We'll provide a CloudFormation template to set up the tutorial environment. After creating the stack, we configure output data in the game instance and look up the Cognito user pool in the nested stack since we're using a nested setup. Each nested stack represents a different system, and the main stack links them together. The MMO server side, written in Python with Fast API, is deployed on an EC2 instance. I created 2 Cognito accounts off screen. And you can see that when the second player logs in, an AI character loads up for the first player. A few seconds later, test user 2's AI character appears in test user 1's client. After each player moves, their AI character moves in the other's client. This isn't real time, but setting the tick interval in the player character to 0 and position update interval to 0 in the Python code would make it real time. When test user 1 goes offline, the AI character in test user 2's client disappears. And that's it. Thank you all for watching.